Deep neural networks are remarkably effective at generalizing, but the exact mechanism behind that success remains one of the most active areas of research in machine learning. One of the most influential frameworks for explaining this phenomenon is the information bottleneck principle. It proposes that during training, networks learn to compress their input representations by discarding irrelevant details, while preserving only the information necessary for the downstream task. But here's the critical ambiguity. What does compression actually mean in a high-dimensional latent space? For years, the field has operated under a fairly intuitive assumption. Information theoretic compression and geometric compression are two sides of the same coin. Information compression is quantified by mutual information, tracking how much information about the raw input survives in the latent layer. Geometric compression is typically measured by neural collapse, which quantifies how tightly the representations for each class cluster together in space. The prevailing wisdom was that as mutual information drops, these clusters should naturally tighten. Tighter clusters, lower information content, better generalization. It felt like a unified theory. But a recent paper by Adilova, Petska, Fisher, and Geiger puts that intuition to the test, and their findings fundamentally challenge the standard narrative. The central question is straightforward. Does low mutual information actually guarantee geometrically compressed, tightly clustered representations? And if not, what is really driving the relationship between these two metrics? To answer this, the authors set up a rigorous empirical and theoretical framework that covers the full spectrum of stochastic regularization. They examined two fundamentally different noise injection schemes. First, conditional entropy bottleneck networks, which use additive, data-dependent noise. Second, networks regularized with Gaussian dropout, which applies multiplicative fixed-variance noise. By sweeping across these architectures, they can independently probe how information flow and spatial clustering interact, without conflating the two mechanisms. Before diving into the experiments, there's a crucial theoretical hurdle. In deterministic neural networks with continuous weight distributions, the mutual information between inputs and representations is mathematically provable as infinite. That makes it useless for practical analysis. The authors address this by extending a previous result on ReLU networks. They prove a formal theorem. Any neural network using continuous dropout with real analytic activation functions, like Sigmoid, TAN, or GELU, guarantees finite mutual information. The proof relies on the Logiciuc structure theorem. Because analytic functions have zeros that form lower dimensional varieties of measure zero, and because the Logiciuc's inequality bounds the function's behavior polynomially near those zeros, the expected log density integral remains finite. This isn't just a mathematical footnote. It establishes a rigorous foundation for applying information theoretic analysis to modern architectures that were previously off-limits due to theoretical vacuity. With finite mutual information guaranteed, the next challenge is estimation. For the CEB models, the mutual information bound is baked directly into the training objective as a variational upper bound, so it's available at no extra computational cost. But for the dropout models, they need an external estimator. They deliberately choose the difference of entropy's estimator over alternatives like mine or club. Why? Because DUI provides a stable, finite sample lower bound on mutual information by separately estimating the marginal entropy of the representations and the conditional entropy given the inputs. Using a factorized logistic mixture model, it avoids the convergence instability and batch size saturation that plague contrastive estimators in high-dimensional spaces. For geometric compression, they measure the neural collapse statistic, specifically tracking the ratio of within-class variance to between-class centroid distances. A low NC value means tight, well-separated clusters. A high value means diffuse, overlapping representations. Now here, that's where the experiments get interesting. To map the relationship between these two compression types, they can't just train standard models. They need to systematically vary the trade-offs. For CEB, they sweep the beta hyperparameter, which controls the weight between classification accuracy and information compression. Low beta forces heavy compression at the cost of accuracy. High beta prioritizes accuracy, allowing more information to flow through. For dropout models, they can't just vary the dropout rate without breaking training stability. Instead, they introduce a geometric regularizer that explicitly penalizes or encourages clustering, sweeping a lambda coefficient to force models into underfitting, standard, and overfitting regimes. They run this across dozens of models, including MLPs, LeNet, wide-range nets, dense nets, and mini-BERT, spanning vision and NLP tasks. Then they compute rank correlations between mutual information, the NC statistic, and generalization performance. The results consistently break the old assumption. Instead of a positive correlation, they find a strong, negative, and nonlinear relationship between mutual information and geometric compression. High mutual information often coincides with tight, well-clustered representations. Conversely, heavy information compression in these setups frequently results in highly noisy, dispersed representations with weak clustering. Why does this happen? The paper illustrates it with a controlled toy model. Information theoretic compression can be achieved in two completely different ways. You can reduce mutual information by making the encoder extremely noisy, which blurs class boundaries and destroys geometric structure. Or you can reduce it by making the encoder extremely precise, which tightens the clusters. The NC statistic only captures the second case. So when you're sweeping regularization parameters, you're often moving along the noisy, high NC, low MI axis, which naturally creates a negative correlation. But the findings don't stop there. The correlation isn't even stable across different training regimes. In certain configurations, particularly when the model's generalization behavior shifts, the sign of the correlation flips. Underfitting models show one trend, well-generalizing models show another, and overfitting models reverse it again. This strongly suggests that mutual information and geometric compression aren't directly causing each other. Instead, they're both being driven by a third variable, the model's generalization capacity. The authors frame this through Reichenbach's principle of common cause. Generalization acts as a confounder, entangling information flow and spatial geometry in a way that looks like a direct relationship until you control for it. So what does this mean for representation learning? First, we need to stop treating mutual information and geometric compression as interchangeable proxies. They capture fundamentally different properties of the latent space. Second, claims about generalization based solely on information plane analyses or clustering metrics need to be treated with caution. Third, the information bottleneck isn't just about shrinking clusters. It's a more complex trade-off between noise injection, feature preservation, and task-specific structure. This research doesn't just correct a misconception. It opens up a new direction for causal analysis in deep learning. Moving from correlational plots to mechanistic understanding of how regularization, noise, and generalization interact will be critical for designing more robust foundation models. If we want to understand why deep networks generalize, we have to stop assuming that information compression and geometric compression are the same thing. They're not, and mapping the true structure of their relationship is one of the next big steps in making deep learning more predictable, interpretable, and controllable.